Okay, good afternoon, everyone. Welcome. So we are at the second half of this semester, and this is exercise session 8, and we have quite a bit to cover this session. So without further ado, let's get into it. So today, I'd like to cover mainly two topics. I'd like to go through two topics with you, specifically Yarn and Spark, right? And for Yarn, we are going to talk about what it is, its architecture, and its essential components, what they do, and how they orchestrate together as a whole. And we are also going to talk about some selected exercises. There are a lot, so I won't go through every single one of them. And also after, I think, going through some of the essential concepts, those questions shouldn't be a problem for you guys. And then I will cover some Spark concepts, how it's organized, especially the RDD, the design principles, the caching mechanism, and the partitioning. And finally, we're going to look at some coring options. Okay? All right. Just before I got started, I've received still some emails about where the nodes are located. So basically in the repository, and there's an annotated solution folder, and you can find all the nodes uploaded for the sessions, okay? I will do that right after the session. So first, so I think first I'd like to just to jog your memory a little bit about what we've discussed in the last session, which is nothing but MapReduce, right? But essentially what we've covered is that MapReduce has this centralized architecture that we've looked at a million times, and the main bottleneck, as we've discussed, is really this piece of daemon, right? It's the job tracker, right? It's responsible for scheduling and running the task, as well as tracking the progress on each and every single component, right? So not only running them, but also scheduling them on different nodes. So it's quite a bit of work, and it would be great to separate this concern to different components, right? As we typically do in software engineering. And that is what Yarn was designed for, right? So what Yarn is nothing but a separation of concerns, right? So in this case, as we can see, so on the left-hand side, you have the MapReduce version 1, Haboot version 1 and version 2. And the essential difference is really that in version 2, what we did is that we split MapReduce into two parts, right? So we split the resource management and the data processing, right? So the data processing is still here, but for the resource management, job scheduling, or other junk is separated into Yarn, right? So we basically blow this MapReduce, the single piece of system, into two parts. So this is basically the separation of concerns, right? And what this brings us is great scalability. So according to Hadoop, in version 1, what we have is approximately 5K nodes, maximally. And on this 5K nodes, we maximally can have 40K concurrent jobs or tasks instead running, right? And this is at the time from Yahoo. But on version 2, because of this separation of concerns and the separate handling of resource management, we can scale up to 3x, so about 15K nodes and tens of thousands of jobs, tasks. right? So this really gives us great scalability, and 5,000 nodes is really nothing in the current day for the current day applications. Okay. Any questions? And also, since we have another layer, which is the data processing layer, so we have now many more layers. So on top of the abstraction, so the data processing abstraction, what we can do is that we can run Spark, we will look at later MPI, graph processing, what have you. Okay, so this is basically how computer science is progressing, right? We're adding more and more layers of abstractions or interactions in order to build on top of each other without rebuilding the wheel that's being created before, and yeah, take advantage of the existing infrastructure. Question? Yeah.
What specifically does data processing refer to?
Yes, so in terms of, the question is what data processing really means in this context. So it's application specific. So for MapReduce, it would be the map tasks and reduce tasks. For Spark, it would be all kinds of transformations and actions. But yeah, Spark is a generalization of MapReduce, but basically it's the pure computation without worrying about how many cores I should allocate to my tasks, and how many memories we should allocate. So
you just send your tasks or the application beyond that take care of?
Exactly. So it's like you're writing your application, your Python application on your laptop without writing half of the Linux kernel, right? So you can think of Yarn as a Linux kernel, and HDFS is one of the subsystems, file systems, for example. Right. That's not an accurate analogy because, like Linux is monolithic, so everything is integrated. So for 1.1, you're supposed to list 3 shortcomings of MapReduce. In the interest of time, I've added more details to the official answers in terms of why Yarn is better than MapReduce v1. But we've briefly discussed the bottleneck of the job tracker that we've just talked about, the scaling and the types of applications you can run on Yarn versus on MapReduce, and as well as resource utilization. But you can look at it offline when you have time. Okay. Right. Next, we will be looking at the architecture of Yarn. So I've stolen again a screenshot from the lecture. I find it's quite intuitive, but I've got to make some modifications. But basically, again, we still have this centralized architecture, right? Instead of having a job tracker as the daemon, now we are having a thing called resource manager. But essentially, they are the same, right? They have a global view of the whole the whole cluster in terms of the resources, the tasks, the progresses, and so on, the status. And we have the node manager here. So what node manager is, as you can imagine, this is really nothing but a generalized task tracker, as we've seen in the previous session, right? So previously we have here the job tracker here, but in this case, because Yarn is built on top of HDFS or this decentralized architecture, this is really nothing but a generalized, let me add a quote. Generalized task tracking. It's tracking the progress of every single container running on the corresponding node. Okay. And the green boxes, I'm going to say, so each of the green boxes is going to represent, so in this case, this is going to be a slot, right? Or a core of a CPU. Okay, it's a bit weird to have an odd number of cores on a computer, but yeah, in this case, for this animation or for this figure, we have, say, 3 cores per node. meaning that we can run 3 kernel threads on each of the machines. Okay, and then
isn't that the container?
uh,
Have multiple cores.
right. So yes, so that's a container in the lecture, but I'm gonna call it cores as a more general concept of resources that we can allocate. But basically, it's a slot. It can also contain, so each CPU is attached with a bunch of memory banks, but maybe in this case, you have 1 core with some amount of memory. So in that case, it's a general concept of threads. But indeed, so for example, in this case, we can group these 2 cores, say, oops, this is a container. Don't be confused with this container with the Docker one, right? This is nothing. Well, it can be a Docker container if Yarn is hosted on Kubernetes, but in this case, container is really a group of resources, just a group of resources. A Docker container is also a group of resources, but here is a more generalized concept. Okay. Then we have the client. Client submit a job to the cluster, so to the resource manager specifically. And in this case, the resource manager really contains essentially two pieces of code. Basically, the first one is so-called the application manager. Bit too. Let's simplify it a bit. Right. So first, the client submit the job to the resource manager, accepted by, maybe we should change the color. So this is step 1 by the application manager. So the responsibility of application manager is really twofold. One is it admits new jobs. And basically this is concerned with security checks. For each job, it comes with an ID, and basically it checks whether this job has been submitted or not to prevent some malicious behaviors, okay? And the second thing is that it also is responsible for collecting the finished jobs and its logs. Okay, so when the user says, okay, I executed some jobs last month, I want to look at the logs and some results even, give it back to me, then the application manager is in charge of that. But this is really FOI because it's not very essential to this course. But another piece which is more essential to us is the scheduler. By the way, there are a lot more other components, but these are the 2 most important ones. So the scheduler is really like what we have. It's having a global view of the whole cluster, right? It knows how much resources have been used on each of the nodes so that it can make an optimized resource scheduling. And so upon the admission of the job, the scheduler will say, okay, and now I need to have someone handle this job for me, right? This is so-called delegation. It doesn't handle every single job submitted to the cluster, otherwise it won't be scalable. So it delegates the job management to an application master, say in this case, okay, I will contact the node manager in this case and says that this container, I promote you to an application master. Okay, so now this container having 2 cores is going to manage the job that's just got scheduled to the cluster. Okay. And so this is step 2. And what maybe here, and what application master would do next is that, well, given the jobs, so it will inspect the job to see what kind of job this is. If it's a heavy lifting job, maybe it requires GPUs, a bunch of CPU cores, then it will so-called negotiate the resource with the application, with the resource manager. So this step is a bit clustered already. Let's change the direction. Step 2, this is step 3, and step 3 is resource negotiation. Okay, and this is the responsibility of application master, right? And then the scheduler receives the request. Say in this case, I want 3 CPU cores, so 3 cores. I don't know, 30 megabytes of memory is quite a small application. And then what it does is that, well, maybe it's a bit too small. And then the scheduler will look at the whole cluster and say, and run a bunch of scheduling algorithms to filter out the feasible nodes. And in this case, remember that we want to maximize data locality as we talked about last time. And everything is built on HDFS. So maybe the data we're operating on is located on 2 nodes, right? Say this is data node 1, 2, 3, and this is data node 4, and we have 1 block of data, B1 here, and we have block of data located on D4, right? And so since we have 2 pieces of data located on these 2 nodes, so of course the optimal choice would be send the computation closer to the data. So in this case, it's very likely, that say, okay, the cluster say, I want to dedicate these 2 cores as container 1 and this 1 core as container 2. Okay, so this is the 4th step, scheduling of resources, and we want to maximize data locality. Again, right? In the big data regime, in the grand scheme of things, we really don't want to move data as much as possible. Okay, and the next step would be, okay, application master is notified that these containers already, or resources, have been reserved for the application master. Now, what the application master will do is that it will go contact the 2 data nodes. Go contact the data node, but the node manager. So node manager basically is nothing but the daemon still running on each node. Okay, so in this case, it's contacting these 2 nodes. This is step 5. If the numbering is correct, I think so. Yes, and then it will says, okay, let's start the job. Right? And then what node manager would say, okay, now we've received the message from the application master, and we will start the job. So this is also step 5. Okay, this is launching. I can do better than that. Okay, launching the container on the actual machine. Right?
It doesn't know the job.
Question?
It doesn't know the job. You haven't told the node manager what the job is.
Right. So the question is, does the data node does the data node know whether what kind of job this is? So it knows the kind of computation is going to be performed. For example, it's a transformation, it's a map task, or reduce task. And this will be because you need to send the program basically to the resources allocated on those nodes. So yeah. Right. Let's continue. So now the jobs are running. What the next step would be doing is that application master. Remember, so now it's responsible for managing, running, and tracking the status of these tasks. Okay. So now we have two tasks: task 1 here, and task 2 here, right? And the way it tracks the job is by what? How does the application master know how the progress of each task?
Heartbeats.
Right, heartbeats, exactly. So the progress of these tasks is tracked by heartbeat signals, which is by default sent a few seconds, every few seconds. So in this case, what we have is that we have this back and forth, sorry, yeah, you can have this message. It's a bit clustered, so let me draw a heart. So what Node Manager will do is that every few seconds, Node Manager will send heartbeat signals to a resource manager, reporting the progress of every single container running on the nodes. Okay, so the resource manager would know, have a global view of the status of all the containers on the tasks. On the cluster. So it acts as, for example, etcd in Kubernetes as a centralized data store, recording all the states of every single container, if you can remember from some previous sessions we've talked about. So the whole cluster has to operate as a global state machine, consistent state machine. And these heartbeat signals are responsible for transmitting the states back to the centralized store. And then by the same token, let me see, yes, these status, the application master will also send periodic heartbeats to the resource manager, and these information about those containers will be picked back to the application master as well. Okay, let me draw a heart. So this is how application master knows, let me check, yeah, the progress, oh gosh, of this job. Okay, say this job has done 60%, and this is the 6th step, is tracking the progress. Okay. Questions? All right. Once this job has finished, right, say we're at the finish line, 100%, this is the last step. Basically, the node manager would notify resource manager saying that, okay, these two containers have all finished, the job has finished. Then the application would know via this indirect messaging, and then this job will be, the logs and the status will be collected back to the application master. So it's finished. Okay, it's a bit clustered, but hopefully you follow along. Any questions? Yeah, question.
Before the 4th step and the 5th step, the resource manager will communicate with the application master?
Will the resource manager communicate with the application manager?
Between the 1st step and the 5th step?
Between the 1st step and 5th step.
Yeah.
Yes. So between the 1st step and 5th step,
Fourth step.
this one.
Yeah.
All right, scheduling the resources,
Yeah.
right? Yes, it will have to communicate with the application master. For example, to notify that the resources are available now. So that's it's still via heartbeats. So the heartbeats is not necessarily a step, but it's there once application master is allocated to a container, and this heartbeats will start from there already. So the communication is constant for updating all the status in the cluster. Yeah. All right. Question.
Yeah, I was wondering, in the progress bar,
Mhm.
how does the application master know the status of the jobs?
Right. So, so the question is, how does the application master know the progress of the jobs? So this is, yeah, that's a good question. So this is a kind of a imprecise. So you can think of this progress bar as discrete steps. Each step represents a container. So if a container has finished, the progress bar would move to, say, there are two jobs and two containers or two tasks in this job, and if one has finished, then this will be moved to 50%. But this is just an intuition as to. But I think, yeah, what you are asking is the status. I think the status is binary. Either it's finished or it's unfinished, in progress. Yeah. Good question. Any other questions regarding the operations? Nope. Alrighty. Then we will move on to, yeah, so I've also added more details about the responsibility of every single component in Yarn, like for example, resource manager, node for global resource scheduling, and node manager we've talked about, application master, containers, and also for the admins, they will be having a web UI to click on for managing the resource and monitoring how the tasks are progressing. And yeah, so you can look at it offline when you have time. All right. All right. Yeah, there are also more details about launching the job. I've just drawn from starting the job to resource negotiation. I've added step by step what each step is doing. But yeah, just take a look at the notebook or the notes offline. Okay. Right. So. And for task 1.2, I think after going through the resource scheduling, it's good to do a few questions to test your knowledge. Yeah, so let me check if I have more things to discuss. Yes, so for these tasks, it shouldn't be a problem. So we just quickly go through them. So for the first one, a resource manager is responsible for providing for tolerance across the cluster. Is that right or wrong? Wrong. Right? Why? Who is responsible for tolerance of those resources across the cluster? Application master? And node manager and
HDFS.
brilliant. Yes. So it's not the resource manager's responsibility for the fault tolerance, right? Otherwise, it's going to be inundated with all the requests, and if this container has died, and we need to do this and that. So this is wrong. For the second one, we have it's asking container allocation. The allocation can take place in a dynamic fashion as the application progresses. Right? Wrong. Yes, exactly. This part is right. Because yeah, so basically in terms of MapReduce, what an application manager would do is that for map task, if you can recall, everything is dynamic, meaning that given the amount of number of map tasks, it will negotiate the resources with the resource manager. And after that, after all the tasks have finished, it will then schedule the reduced task and so on and so forth. It's very dynamic. Instead of allocating everything ahead of time, occupying the slot and making the resource utilization very poor. Okay. The third question is, Yarn plans to allow application to only request a resource in terms of memory and CPU. Is that right? Wrong.
You also have DC network IO.
Exactly. So in new versions of Yarn, you can also have GPU resources, disks, and so on. Okay. For the fourth question, communications between node managers and the resource manager is heartbeat based. We've talked about this. The fifth, a resource manager doesn't have a global view, which is obviously wrong. We don't need to read the rest of it. And then the last one, resource manager has the ability to request resource back from a running application. Right or wrong?
That depends on the scheduling algorithm used.
Yes, that depends on the scheduling, but in general, it's right. So this is something called resource preemption. Oops. So what this means is basically it's preempting resources based on some scheduling algorithm or priorities or fairness. Oops. Although fairness is really a controversial topic to talk about in the context of cloud. But basically, you can preempt resources based on different criteria and so on. All right. So this is task 1.2. I think it shouldn't be a problem for you guys. I've added more details for the explanation for each of the questions because I found the solutions don't contain more explanation. So basically, for example, for the first question, you have node manager and application master and HDFS for handling failures across the cluster, and also different resources you can have in Yarn, and also you have different resource preemption strategies I've added. If you're interested, have a look at it. For example, queue-based preemption, dynamic resource demands, and so on. And yeah. All right. Moving on, if there is no question. Task 1.3, which also should be a piece of cake for you guys. So fault tolerance of running application, who is responsible for that? Resource manager, application master, or node manager?
Application master.
Yes. So basically, whenever you see applications, this should signals the responsibility of the application master. Okay, node manager is also responsible for fault tolerance, but it's monitoring at the node level. Okay, meaning that it doesn't know the concept of application. It doesn't have a clue about which task belongs to which application. It only knows that there are containers running. So this is node. Okay, this is node level monitoring, right? And second, asking for resources needed for an application. Again, application master. So we've talked about this is the resource negotiation. Okay. And providing leases to use containers? Who has the authority to say that you have the right to use that container? Yes, resource manager. It does nothing but managing resources, as the name implies. And then tracking status and progresses of applications, of course, application master again, right? So these four are pretty trivial, but lastly, we have a bonus, as always, handling container failures. Who is or who are responsible for that? Instead of at the application level, what if a container failed? So that container is running my reduce task and it died. What should I do? Sorry? Node manager. Anything else? Resource manager, yes. Anyone else? And application manager. Yes, I was also quite surprised because, so actually handling, so I would say the first question is not very precise in my point of view, because actually for handling single container failures, you need 3 parties to participate. Specifically, for example, I have a container that runs some jobs, for example, a reduce task, and in the middle of the running, say hardware failed or network partitioned, right? I can't contact this container anymore. And the node manager, if the node manager is still alive, right, will be tracking, right? You can think of this as a watch loop, right? In most of the applications, you will have some watch daemons watching the cluster. In this case, this daemon will watch this cluster, this container, and this has failed. What this does is that, well, it will communicate with the resource manager via heartbeats, right? And resource manager would know, okay, one of the tasks has failed. And then resource manager will piggyback this information also via heartbeats. Ah, gosh, it's hot. With the application master, right? The application master would know one of the tasks of this application has failed. So there are, of course, many strategies you can write into application as to how you can handle a failure. But in this case, maybe the application master wants to rerun this container, then the resource manager will allocate a new piece of a new container of the same amount of resource on the node manager or a different node manager. If that node manager has also died, then this is a new container, and then the resources needed is available. But whether or not application manager decides to use it, it depends on the policy. But for example, in this case, it wants to restart the job, then it can say, okay, let's restart. So this is how you can recover. You can recover from a failure. Right, this basically repeating what we've just had. Yeah, so it really requires all hands on deck to handle this failure. Okay, so typically on a high level, you can say, well, on the application abstraction, it's basically the application master's job to determine whether or not to restart a task in order for this application to proceed. But actually, at the lower level, all parties should participate. Okay, any questions? All right, so next, so there are a lot more details about the bonus question, and you can have a look at it, how it's retried, and what each component is doing offline, okay? Next, if there are no more questions, we're going to move on to Spark. Right. I think Spark is in general a very exciting topic, and is still the having a heavy lifting framework nowadays, right? Every time when it comes to cluster computing, you've got to deal with Spark, regardless of which level you are dealing with. And Spark is really a generalized multi-stage MapReduce, if you like. And so to run Spark, so this is from the documentation of from the official documentation to run Spark for every application. You basically have, so this is my app, and then you have a driver program basically using the application API to talk to the Spark context. Basically, this contains a bunch of connections. So this is for communication. Oops, if I can spell. This is for communication with the cluster components, right? With the nodes, with the manager, and this is the client we were talking about, right? And then the cluster manager will handle the job, the scheduling the job, the resource management. So this could be Yarn that we've just introduced. One of the cluster managers, it could be Kubernetes, or could be, I don't know, Mesos, Apache Mesos, and so on, right? It's quite general. Spark can technically run on any cluster managers under the sun. But yeah, so in this case, we will be talking about Spark running on Yarn. All right, and these are the tasks, but in this case, these tasks are more general than just map and reduce, right? Yeah, question?
Does the application must have run on the driver program then, and not in the cluster?
Yeah, the question is where does the application master run? Yeah, so in this case, it's typically on one of the worker nodes instead of co-locating with the application itself, with the client itself, right? So the application is the client of the application, right? So you have the client server architecture, and you send the program as the server part to the server for the server to execute. So yeah,
Okay.
right. Any questions? All right, moving on. I think the first thing I'd like to talk about, oops, missing a bracket. So is the RDD, right? Resilient distributed datasets. It's quite a mouthful, but it's really what makes Spark, right? So it has two essential components, two design principles. One is being immutable, and another is lazy evaluation. And why it has to be immutable? Like why can't we just, I don't know, have a data set and I modify it and do some transformation on it, and yeah, wouldn't that be more efficient than collecting and then creating a copy and do something on the copy and then so on and so forth? Any ideas? Yeah.
Since it's a cluster, it's not always possible to do that, and also you can have the same RDD being the input of many transformations, so you cannot really work on the same one. You need to create copies anyways.
That's a really good point. So just to quickly repeat, so he's saying that the reason is that, in a cluster, it's not always possible for operating on the original data, like the single copy, right? So for example, if we can split this data into multiple copies, then we can say do multiple transformations on different components. That's exactly one of the reasons I like to talk about. Yeah, so in terms of parallel computing, it's more beneficial to take advantage of multiple replicas. Another essential reason I like to cover is, for example, this is an RDD1, this is RDD2, 3, 4, 6, 7, 8, and then the reason, another reason for having these immutable RDDs, so these one RDD could be a collection of objects, okay? So it can contain many different data items in it, and this can be distributed to different components as well. But for example, I want to do a transformation, right? I want to do a transformation on RDD1, and I got RDD2, right? And in this case, I do multiple transformations, and I got 3 and 4, and finally, we aggregate them into 5. So in this case, what if, right? What if what if we've lost 5, right? For example, one of the data nodes or some of the data nodes happen to fail. All the data nodes allocating RDD5 have died, right? So we've lost this piece of data. By having these immutable objects, what essentially are doing is that we're keeping multiple versions of the recipes of making RDD5 so that we can directly go from these recipes to RDD5 instead of going back to the original data and to reproduce the whole thing from the beginning, right? So in this case, if we were to modify RDD1 from the start, then if 5 failed, meaning that we only have a single copy, then we need to do all the things, this part again, right? This is very inefficient because an RDD can have gigabytes of data and it takes days to compute and you don't want to lose that. So basically what we are having is that we are having in a Spark, Spark's terminology is we are having this lineage or the graph or the DAG to make sure the resilience. We can recompute, we can recover from failure whenever we want in the most efficient way, right? And this is similar to the lazy evaluation, right? So for lazy evaluation, the reason why, say, we are at the end of the computation and everything, so these are transformations, okay? What transformation does is nothing but creating this lineage, okay? You're doing a map, you're doing a select, or reduce, sorry, not reduce, but other like transformations, they are nothing but creating or drawing, you can think of it as a brush, to draw this computation graph, to draw this lineage graph. But only it's only when we like invoke an action does the cluster starts doing something, right? The reason being that once the cluster has this global view of the computation, it can optimize the computation to avoid like redundant calculation. For example, I've computed RDD6, and when I am computing RDD7, I don't need to recompute all this stuff. The only thing I need is to take RDD5 and to compute from there. And same goes for RDD8, and I just take RDD5. Right? So if you were to say, okay, I want to do this eager evaluation, and for every step I just execute the whole stuff because the cluster doesn't have the graph in memory saying that, okay, actually you can go from here and cache this value already. Right? So this is why we have this lazy evaluation for optimizing execution. Any questions? Right, you can think of intermediate RDDs as the versions of different computation at different computation stages, and yeah, given different versions, you can derive the final results more efficiently and or recover from that. Okay. Right, moving on. So yeah, given the time, so why Spark is much faster than MapReduce, I will not go into detail about it. I've provided some answers in terms of in-memory processing, like the old school techniques employed from Dremel all the way to Spark. You can look at it, the DAG's execution, I've talked about it, resilient, RDDs, lazy evaluation, more APIs and libraries, stuff. Okay, take a look at it offline when you have time. Right, the next part is those transformations and actions. I would highly recommend play around with it. I think it's quite interesting to look at those actions and transformations. Although I'm not sure how faithful the Python implementation is compared to the original Scala ones, but you can get a sense of, for example, how different transformation map, filter, flap map are doing, and different actions, for example, collecting results, counting, taking the first a few results. And you can, previously actually people start by creating Spark context, but nowadays we have already moved on to Spark sessions. So basically Spark session has preceded the Spark context. And then you can create RDD from files or from a list of values. And get familiar with the syntax. So these are the functional APIs for transformation and actions. These are the lowest level stuff. And we'll look at more high level APIs later. Okay. Right. And next interesting stuff is explicit caching of intermediate values. And as I've shown, the value of caching in intermediate RDDs for saving computation and memory as well. Sorry, not memory necessarily, but saving computation. But once you've done a job, the intermediate value will be thrown away automatically. So if you want to, you know that the next job will reuse some of the RDDs in the previous job, then you need explicit caching, right? So in this case, I've modified the example so you can use, for example, the fruits basically are the ones that I've created from the file, the RDD, and then you can explicitly call cache. So this is the persist API with the memory only option. So this will cache this RDD, the fruits, in memory. So if you print out the solution, it's not a solution, the result will find that the fruits RDD is cached in memory. In what ways? It's cached in memory in a deserialized object, and also is cached in a serialized GVM specific format in memory, and it's replicated one time. Okay, and if you unpersist, this will be removed from memory, but the serialized object is still in the memory because we are using a notebook. And similarly, for example 2, I've added a thing called memory and disks. So by passing this option, what we are doing is that we are persisting not only in memory, but also in disk, replicating this object twice, right? So if you print out the result, you will find that it's cached in both disks and memory, serialized object as we had before, and then we have two replicas in the class, two replicas on 2 nodes. Okay, and the difference between these two is that when it's serialized, when it's deserialized in memory, it's typically larger, the RDD, but you don't pay the price of deserializing it when using it. So this is more efficient than serialized object in memory, but it takes a bit of time to deserialize the objects. Okay, and yeah, feel free to play around it. I'll push the modified notebook as well. Okay, any questions? Right, moving on. We have RDD partitioning. So the first question for you guys, why? Why do we need partition a single RDD into to different nodes, for example? Maybe these two figures ring a bell. Parallel execution and yes, reducing shuffling, right? Exactly. So one is parallelizing the task exactly. The second is to reduce the shuffling. So for example, the final results, if we know the final result is organized by key, right, from key 1, key 3, key 2, key 3, and key 4, then if we were to partition this RDD, so this whole thing, you can think of it as this is an RDD, and we have 3 stages, right? We have stage 1, 2, and 3. And if we were to know that, okay, the final results will be computed based on the keys, then would be great to separate, to split them ahead of time so that we can avoid the additional network traffic between these stages. Okay, so partitioning is basically to reduce, shuffling. And we have less network traffic, and the performance goes up. Right? And I've had some examples modified from the notebook. So basically, in this case, what we're having is that so I'm creating an RDD called pairs from a list of values. Okay, so basically a list of key-value pairs. So in this case, this is a single RDD with a single partition. So it's not partition at all. And we have the keys, and we have the values. Right? And then what we can do is that we can do some hash partitioning, which is the default. I'm using the Python hash, but by default, Spark will use so-called portable hash, but it's basically the same thing. So what we're doing is that, okay, we're creating, sorry, I'm creating it again, but yeah, so we're, for this RDD, we're partitioning it to 3 partitions using this partition function provided, which is basically a hash, right? So the result would be 3 partitions, and each of which would contain, so we have, yeah, 1 partition, 3 partitions, and each partition would contain the same key. Right? And so this is hash partition, and we can do similar stuff as we've done. We can do similar stuff as we've done in, say, those white column stores. We can do range partitions. So in this case, the function we're providing is based on the key value. So we're partitioning it basically a binary partition function if it's greater than 1 or not. And the resulting, so because we are forcing it to be 3 partition, still 3 partition. But in this case, we're having 1 partition, 2 partition, and an empty partition at the end. Right? So basically, these are the keys less than, these are the keys, yeah, less than or equal to 1, these are the greater than 1. But basically, what you can do is that, yeah, if you can recall from the white column stores, you are given these different partitions to different region servers, for example. So it's more or less the same idea. So you can have different partition functions, okay? And you can also have your own partition functions. So I was just playing around with this. It's quite interesting. And the last thing I'd like to, any questions for this partitioning? But for this to work, you really need to know the kind of computation you are performing, right? Otherwise, you wouldn't, you wouldn't know very. But still, so even if you don't need, you don't know specifically the kind of computation we'll get, still it's recommended to partition, at least first for load balancing, right? To load balance the workloads to different class nodes. Second, the cluster will have the metadata on the RDDs, so that the cluster knows approximately which part of the data is located where, so that when it's done doing the computation, it doesn't need to go through the whole cluster to find the data blocks everywhere. Okay. Right. Next, we'll have just briefly talk about the RDDs, the DataFrames, and datasets. Right. So basically, they are introduced from by different versions. I've listed a markdown table here, but basically, they are introduced at different versions, and they are having increasingly higher abstraction. And what they are in common is that they both handle both structured and unstructured data. They can handle tags, CSV, JSON, Parquet, and they are all immutable and lazy. Okay, and the only difference is the API they're having, and these are basically. So for example, with RDD, if you really know, right, you are very experienced programmers, you can use RDD. But otherwise, I would highly recommend using the DataFrame and Datasets APIs. So these are more high level instead of using the functional APIs. And but it depends on, for Scala, for some languages, DataFrame is just an alias for the datasets. And for different data formats, you can use either the functional API, as I've said, in the exam or in your daily job, for example, to filter, for sort, select, or you can use the structured API. Or, for example, just by providing the Spark SQL. And I would highly recommend using this. This is really a declarative, if I can spell, programming. And you are giving the Spark, the underlying framework, the option to optimize, to create a query plan to optimize your query instead of doing it by hand yourself. This is, this is still a DataFrame, so this is not functional. The functional ones I think I've looked at is the map, here, yes. So the map, the map, the filter, the union, right? The reason why I don't recommend using this functional API is that you are not telling the cluster or a Spark explicitly what you are doing, right? You are doing a filter, or you can combine these functions as you've seen in the notebook to create some MapReduce-like computation. But you are not telling the cluster that I want to do a MapReduce. So the cluster doesn't know what you are doing. Therefore, it can't really optimize your computation. Instead, for example, in this kind of Spark functional API, you're telling I want to select certain columns from the data sets on which column and so on. And you're giving the option, the cluster option to optimize and create a plan. And typically, the plan they create is much more optimized because they have for DataFrame and datasets, your query will be optimized directly by the so-called the catalyst, I think, from Databricks. So this optimizer will optimize your query more efficiently if you tell explicitly what you are doing. Okay, so and I find it's easier to write this kind of a declarative things in the exam instead of trying to figure out how I can map a task, a MapReduce task via filter or like reduce by key, stuff like that. So I think writing a SQL query is nicer, but yeah, that's my suggestion. Yeah, I think I picked the wrong example. This is still DataFrame, but yeah. So I don't recommend using RDD, although it's I've talked a lot about RDD, but under the hood they are all RDDs. But basically, DataFrame and datasets are higher level abstractions on top of it, which is nicer. You always work with higher abstractions as much as possible. Okay, so yeah, that's basically what I wanted to cover. Let me check my list to see if there is anything else. So basically, to quickly recap what we've discussed, we've talked about Yarn, the architecture built on top of, improved from MapReduce, how it works, the step by step. Please give a read for these detailed document. And yeah, maybe there are some typos, but yeah, let me know. And also, we've talked about Spark, how it's organized, why the RDDs are immutable and lazily evaluated, why it gives a competitive edge over MapReduce, and the sort of APIs we are having for partitioning a single RDD, for caching explicitly, and the comparison between different formats. So that's all I'd like to cover in this session. And are there any remaining questions? Nope. Then that's it, guys. I will stick around for any questions you may have from the lectures or the exercises. But yeah, that's it. We've got half an hour back. Thanks a lot.